We have one more example here. Approximate the cube root of 30 using Newton's method. Approximate, accurate to 4 decimal places. Okay. So the first thing we need here is we need some function set equal to 0, right? This is what we need when we're using Newton's method. So the question is, well, how do we incorporate a function? Well, why don't we start off by just actually saying this? Why don't we start off by just saying the cube root of 30 is equal to x. Okay. Now, if you were to say try and move things around here a little bit, you could say, x minus the cube root of 30, and you could say that this here is equal to 0, and you could call your function then x minus the cube root of 30. Okay. While this would work, this is going to rely on the fact that we know what the cube root of 30 is. Well, if we don't know what the cube root of 30 is what we could do instead is we could cube each side of this equation. So that gives us 30 is equal to x cubed. And from there, you could subtract by 30 on each side, and so you get x cubed minus 30. And so this gives us then that our f of x is this x cubed minus 30. Now, the next thing here is again, we're trying to estimate the cube root of 30. I would recommend starting with something that you know is going to be close to the cube root of 30. So something that might help us out a little bit here is to maybe think about what some numbers cubed are equal to. For instance, 2 cubed is 8, and 3 cubed is 27, and 4 cubed is 64. So this is telling me that we should choose x to be somewhere around 3 or 4. Okay, right? It's going to be 3 point something for sure. Okay. But the x equals 3 would be a lot closer than x equals 4, right? 27 is pretty close to 30. So we're going to try that as our x1. Let's go ahead and write that. x1 equals 3. Okay. And it's just because the cube root of 30 is already pretty close to 3. Now let's find x2. So x2 should be 3 minus f of 3 all over f prime of 3. So it might be helpful for us to actually find the derivative as well here. So our derivative, f prime of x, is just equal to 3x squared using our power rule. All right, so next here we have 3 minus, let me write that a little bit neater, 3 minus f of 3. So that's going to be 27 minus 30, which is negative 3, and then over f prime of 3. So if we were to plug 3 into the derivative, that's going to give us 27. And let's see what that gives us here. So that's going to give us approximately 3.111111 and so on. Okay. And I would just store that value in my calculator or just continue using the algorithm. I wouldn't actually plug in 3.111111. Just again store that in your calculator. And now that you have that stored in there, you could then go and compute x3. It should be equivalent to x2 minus f of x2 over f prime of x2. And this should come out to about 3.107237339. And one more, x4. And why do we need one more? need one more because we were asked in this question to have 4 decimal places of accuracy. And as of right now, you can see we've only had 1 digit repeat so far. Okay, we're only accurate up to 1 decimal place so far that we know of. Okay. So let's go a little bit further. And if we do that, it looks like we should get x4 is equal to 3.107232506. So we can up this accuracy now. So we have 10723 in common. And so that means we have 5 decimal places of accuracy. Okay. And so if we were to record what the cube root of 30 is approximately equal to, and you can verify this on your calculator, it's approximately equal to 3.10723. Technically, I didn't need to write the 3 there, but since we know it's accurate to that spot, let's write it. All right, and one last thing I want to point out is we had to do what? 3 calculations, one for x2, one for x3, and one for x4. And in just doing those 3 calculations using Newton's method, we have something that's actually accurate up to 5 decimal places for the cube root of 30. So this is a pretty efficient algorithm, or a pretty efficient technique.